Welcome back. I'm Professor Steele, and today we are going to do another thinking problem. This is an extension of our vectors in aviation. This given scenario is that we're traveling from International Falls, Minnesota to Bemidji, Minnesota. The pilot needs to fly at a heading of east 225 degrees north. The plane is flying the route at a speed of 120 miles per hour at a fixed altitude with no wind factor. But at a certain point, the plane will experience some wind with the velocity of 45 miles per hour and with a heading of west 30 degrees north. So this is our wind, not written as vectors yet. We're just annotating some ideas that are given in the problem. So part A is requiring us to express the velocities of the wind and the plane as vectors in component form. And you'll notice we're going to call the wind vector W and the plane vector A. So first things are to always sketch a diagram. Our plane, east 225 degrees of north. So here's due north, and if we go east 225 degrees, so 180 would be due south. If we went due west, that's 180 plus another 90, 270. We want 225, so it's going to be somewhere in this third quadrant region. So just so we don't get confused, I'm going to put an arrow on the plane vector, and we know that it has a magnitude of 120. So let's label all the pieces here. There is our plane vector. The wind is west 30 degrees of north. So again, here's north, we're going to go west 30 degrees, roughly in this direction. There's our 30 degrees, and it has a magnitude of 45. Now, what we have to do is give these two vectors in component form. First thing, I'm going to just draw in a horizontal dotted line, because if we're trying to give the plane in vector form, I want to determine what this angle in here is. 225 degrees all the way around. We know all the way to due west would be 270. So this missing angle is 45 degrees. So we have the plane vector set up now as, we have a 45 degree, we have a magnitude of 120. So 120 cosine of, we don't want to use 45, even though that is our reference angle. Cosine is our horizontal measurement and it happens to be negative. So negative 120 cosine 45 degrees. And our vertical measurement, again, it's in the negative direction. So it'll be negative 120 sine of 45 degrees. So that gives our plane vector as negative 84.9, negative 84.9. We know we've done this correctly because the values should be the same. Remember, our 45-45 triangle has the same cosine measurement as sine. So that is our plane vector. Now we're similarly going to do the same thing for our wind vector. We notice that we have the 30 degree angle in here, which means the angle between the horizontal and the wind is actually 60 degrees. So our wind vector is negative magnitude 45 cosine of 60 degrees, and our vertical measurement is positive 45 sine of 60 degrees. This gives us our horizontal measurement of negative 22.5 and our vertical measurement of 39.0. I've rounded to one decimal place since our value is 38.97. So there's our vector for the plane, there's our vector for the wind. If we want to write it in unit vector form, we would have negative 84.9i minus 84.9j for our plane, and for our wind, negative 22.5i plus 39j. We have now got our airplane and wind in vector component form. We now need to find the resultant vector. So we need to add them together. Remember that the plane is going in this direction and the wind is affecting its direction. So we have to move our wind vector so that it is tail to tip. So if you can imagine moving the wind vector so that it is now here. So here's our plane, here's our wind vector, and the requirement is to find our resultant vector. Here is A plus W. And what we need to do is determine what is the resultant vector of the wind and the plane. We've already got our wind and plane, so the resultant vector is simply adding the two vectors. And just like we've done before with vector addition, the plane plus the wind vector, we simply add the components. Negative 84.9 plus negative 22.5 gives us negative 107.4 in the horizontal direction. And then adding our vertical components, we get negative 45.9. So there is our resultant vector, plane plus wind. Typically, as in part C, you will be asked for what is the resultant speed. Resultant speed is simply the magnitude of this vector. We will take our plane and wind vector and find the magnitude. Since this is a right angle triangle, we can use Pythagoras' theorem where we are finding the hypotenuse. And when we do this calculation, we get 116.8. And the magnitude is actually the speed of the resultant vector. So now that we have the magnitude or the resultant speed, we need part D, the resultant direction of the plane. So if you look at our diagram, we are actually trying to figure out in this triangle, what is the measure of the angle all the way from due north? The easiest way to calculate this is if we think about the reference angle created, we have an angle here we can determine since we have the magnitude and we have the horizontal and vertical components of that vector. So recall, to find this angle, we know tan of theta is the vertical measurement over the horizontal. Negative 45.9 divided by negative 107.4. We want that angle, and I called it star, so let me change this to star. So our angle happens to be the inverse tangent. Negative divided by negative would be positive, and this is approximately 23.1 degrees. Now remember, this is our reference angle. We want our direction given in terms of due north. So if this is 23.1, we're going to do some algebra. So we have 270 minus that 23.1. So we are actually 246.9 degrees east of north. So we have now calculated the resultant direction of the plane, and we're giving it in aviation format. The last part of this problem states if the plane is maintaining the speed and direction for the remainder of the flight, which is 65 miles, how long will it take to arrive in Bemidji? So what we have so far is that our resultant speed is 116.8 miles per hour, and we have the distance that we need to cover is 65 miles, and we know if rate is distance over time, then our time is distance over rate. So we are simply going to determine our time by taking our 65 miles and dividing it by 116.8 miles per hour, which gives us 0.56 hours, and we can change this to minutes by multiplying by 60. So let's do some unit conversion. And that gives us 33.4 minutes. So roughly it will take us another 33.4 minutes after the wind has played a factor on the plane to get to Bemidji. I hope this has helped. Thank you for watching. Please make sure to like and subscribe to EdVantage. We'll see you next time.